Alpha Centauri is the closest star system to our own. Yet scientists still do not fully know what may be hidden there. When James Webb finally looked into it, the telescope detected a strange infrared signal that appeared to match a possible planet near a sun-like star. The discovery could have changed the future of space exploration, but when scientists looked again, the signal was gone. No clear error, no confirmed planet, no simple explanation. Today, we explore why James Webb's look into Alpha Centauri shocked scientists. Now, let's begin. 4.37 light-years. That's it. That's the distance between us and the closest star system to our sun, Alpha Centauri. 4.37 light-years. In the context of a universe stretching 93 billion light-years across, that number is essentially zero. That is our next-door neighbor. Humans have had telescopes since 1608. 417 years of pointing lenses and mirrors at the sky. We have photographed galaxies being torn apart by gravity. We have imaged a black hole 55 million light-years away. 55 million with enough resolution to see its shadow. We have detected gravitational waves from neutron stars colliding a billion light-years from Earth. But Alpha Centauri, whether it has planets orbiting around it for 417 years, we had no idea. Let that land. The most technologically advanced species on this planet, with the most sophisticated instruments ever constructed, was completely blind to its nearest neighbor in space. Not the far edge of the galaxy, not some distant cluster halfway across the observable universe. The star system, 4.37 light-years away? That's the equivalent of mapping every continent on Earth in perfect detail and having absolutely no clue what's inside the house next door. Now here's where it gets stranger. Alpha Centauri is not one star, it's three. Alpha Centauri A is the one that matters most for this story. It is a G-type star, the same classification as our own sun. Nearly identical mass, nearly identical surface temperature, sitting at around 5,700 Kelvin compared to the sun's 5,778. Its age is estimated at 5.3 billion years, slightly older than our sun's 4.6 billion, which means if stellar age is any guide, it has had more time to allow planetary systems to stabilize, cool, and potentially develop conditions for complexity. Then there's Alpha Centauri B, smaller, slightly cooler, glowing with a warm orange hue, orbiting A in a binary dance that takes approximately 79.9 years to complete. And then, much farther out, gravitationally bound to the pair but separated by roughly 13,000 astronomical units, is Proxima Centauri, a dim red dwarf. Proxima is actually the single closest star to our sun. At 4.24 light-years, it already has confirmed planets, but those planets exist in a radiation nightmare, bombarded by stellar flares from a temperamental red dwarf. They are not where the real hope lives. Alpha Centauri A is the golden target. Same class of star as our sun, same energy output, same potential habitable zone geometry. If you were designing a star system as a candidate for Earth-like conditions, you would essentially draw Alpha Centauri AA. So why couldn't we see it? You have to know Alpha Centauri is actually how many separate stars, and most people, when asked, say one. The answer to why we were blind for 417 years comes down to one brutal number 10 billion. A star outshines any planet orbiting it by a factor of roughly 10 billion to 1 in visible light, and still hundreds of millions to 1 in infrared. Trying to detect a planet next to its host star is not like finding a needle in a haystack. It is like standing in Los Angeles and trying to see a single candle flame sitting 3 feet away from the surface of the sun. The glare doesn't just obscure the candle, it annihilates it completely. Hubble tried. The Hubble Space Telescope, with all its legendary capability, attempted to probe the Alpha Centauri system for planetary signatures. The proximity of the stars, which you'd think would be an advantage, was actually the problem. Alpha Centauri A and B are so bright, so close together on the sky, that they saturated Hubble's detectors. The system was, paradoxically, too close for Hubble to handle cleanly. Spitzer tried. NASA's Spitzer Space Telescope, designed for infrared observation, took its own shots at Alpha Centauri. Same fundamental problem. The infrared brightness of the two stars overwhelmed any possibility of detecting the comparatively whisper-quiet thermal signature of a planet. The Very Large Telescope in Chile tried. Ground-based interferometry pushed to its limits. Adaptive optics. Every trick in the book. The results came back inconclusive, not confirmation, not denial, just noise. Just the blinding halo of two nearby stars refusing to give up their secrets. Think of it this way. Imagine trying to photograph a mosquito sitting on the lens of a lighthouse beam using a camera phone. The mosquito is real. It's right there. But the light overwhelms everything, and your camera simply cannot resolve the detail you need. That's the situation every telescope on Earth and in orbit faced when they pointed themselves at Alpha Centauri. The breakthrough came from a different direction entirely. Not a brighter telescope, but a smarter one. The James Webb Space Telescope uses a device called a coronagraph, a precisely engineered mask that blocks the light of a target star, creating an artificial eclipse inside the instrument itself. Webb's coronagraph system, combined with its unprecedented infrared sensitivity operating at -233 degrees Celsius in the cold shadow of its sunshield, represented the first time in history that a telescope could theoretically suppress the glare of Alpha Centauri A enough to look for what might be orbiting around it. Theoretically, because even pointing JWST at Alpha Centauri was not a simple decision. The stars are bright enough that engineers had to carefully model exactly how much light would leak past the coronagraph and whether that leak would damage the detectors. Webb was not designed with Alpha Centauri as a primary target. Aiming it there required recalibration. It required risk assessment. It took until 2025 for the instrument team to certify that the observation could be conducted safely with sufficient suppression to make the attempt worthwhile. The most powerful space telescope in human history, and the mission that kept engineers awake at night, was not peering at the edge of the observable universe. It was looking next door. In May of 2025, after 417 years of blindness, the James Webb Space Telescope finally opened its eye and stared directly into Alpha Centauri. And when the first data appeared on the screens inside Mission Control, every person in that room went completely silent. JWST time is not given out casually. Every hour the telescope spends looking at a target represents a zero-sum trade, an hour not spent on something else. The demand from the global astronomy community consistently outpaces available time by a factor of roughly 5 to 1. Proposals go through panels of experts. They are ranked, scored, debated. Only the most scientifically compelling programs survive. The decision to allocate a significant block of observation time specifically to look for planets around Alpha Centauri A, given all the prior failures, given the technical risks, given the competition, was itself a statement of intent. The scientific community was betting that Webb was finally good enough to do what nothing else had managed in 4 centuries. In May of 2025, the data began coming in. The initial processing runs were routine. Engineers and scientists sat with their pipelines, pulling calibration frames, subtracting background noise, running the standard reduction sequences that turn raw photons into usable data. And then, somewhere in those reduction sequences, something appeared that was not supposed to be there. A point of infrared emission, faint, localized, sitting in a position that did not correspond to any known cataloged object in that region of sky. No background galaxy, no known brown dwarf, no previously logged asteroid or stellar remnant. Nothing in the astronomical databases explained it. The team ran the pipeline again. Same result. They checked the detector maps for cosmic ray hits, high-energy particles that occasionally strike Webb's sensors and create false bright spots. Cosmic ray artifacts have a specific signature. They're sharp, single-pixel events with no spectral structure. What the team was seeing was different. It had structure. It had a spectral profile, and that spectral profile was the thing that changed everything. If you were that scientist, staring at that data at 2 in the morning, would you publish immediately? Or would you run it again? Spectroscopy is how astronomy actually knows what it's looking at. Every atom and molecule absorbs and emits light at specific wavelengths, like a fingerprint that cannot be forged. Hydrogen looks like hydrogen. Methane looks like methane. Water vapor looks like water vapor. You cannot fake a spectrum. The laws of quantum mechanics don't negotiate. When you run a spectral analysis on a source of infrared emission, what comes back tells you with extraordinary precision what that source is made of, how hot it is, and roughly how large it must be to produce that brightness. The spectral fingerprint coming back from this new point source matched a gas giant. Not vaguely, not approximately. It matched with the kind of precision that makes scientists deeply uncomfortable, because that level of agreement between prediction and observation usually means one of two things. Either you've found exactly what it looks like, or something has gone catastrophically wrong with your instrument in a very specific and very unlikely way. The temperature reading consistent with a gas giant in the range of 100 to 150 Kelvin at its cloud tops cold, but not impossibly so. The size implied by the luminosity comparable to Saturn. Mass estimates from the flux in the range of half to 1.5 Jupiter masses. The position on the sky placing this object at a distance consistent with Alpha Centauri A, at a projected separation that would put it within or near the star's habitable zone. This was not a detection of a rocky Earth-like world. Let's be precise about that. A Saturn-class gas giant does not itself harbor life as we understand it. But the presence of a large gas giant in a habitable zone carries an enormous implication that the team understood immediately. A planet of that size and position could harbor moons. Large, geologically active moons with liquid water oceans, protected by the planet's magnetosphere. Europa orbits Jupiter in our own solar system, and beneath its ice shell sits a saltwater ocean twice the volume of all of Earth's oceans combined. If Alpha Centauri A had its own Saturn analog, that Saturn analog could have its own Europas. The discovery wasn't just a planet, it was a delivery system for possibility. The team checked the results 7 times over 6 weeks. 7 independent analyses, run by different members of the group using different software implementations of the same pipeline. Every time, the signal survived. Every time, the spectral match held. They pulled in external collaborators and handed them the raw data without telling them what they expected to find. Those collaborators found the same thing. Like a radiologist who spots an anomaly on a scan, calls in a colleague, calls in another, requests the films from a different machine, and every reading comes back the same. At some point, the weight of consistent evidence becomes something you cannot dismiss. The team had reached that point. The technical details they documented were striking in their specificity. The rotational broadening of the spectral lines suggested a spin rate not inconsistent with gas giant rotation in our own solar system. The absence of certain molecular bands ruled out several classes of background objects. The positional stability across multiple observation epochs, the signal didn't move in ways inconsistent with Alpha Centauri A's own proper motion across the sky, tied it gravitationally to the system. The team didn't trust the $10 billion machine. They didn't distrust it either. What they didn't trust was their own disbelief, because finding this would mean finding a potentially habitable zone gas giant around the closest sun-like star to Earth. And that was the kind of result where confirmation bias can destroy careers if you're wrong and change history if you're right. 3 months of internal verification, an emergency peer review process running in parallel, cross-checks with archival data from ground-based observatories to see if any prior hint of this signal had been missed in older datasets. And finally, in August of 2025, they decided to tell the world. The earthquake started the moment the press release went live. The press conference room at ESA's European Space Research and Technology Center in Noordwijk was built to hold 200 people comfortably. On the morning of August 14, 2025, there were 312 bodies packed inside it, standing shoulder to shoulder along every wall, spilling into the hallway, with camera rigs from 47 different news organizations jostling for position. The overflow room next door had its own overflow, and feeding out from both rooms, a simultaneous live stream that within the first 20 minutes of the broadcast had pulled in viewers from 119 countries. The moderator had barely finished the opening statement when the first slide appeared on screen, a single infrared image, false-colored in gold and deep blue, with a faint point of light circled in white against the blackness near Alpha Centauri A. No dramatic music, no slow reveal, just data on a screen and a sentence spoken into a microphone. We have detected a candidate planetary object in the Alpha Centauri A system. The room didn't erupt. It went quiet first. That particular silence, 4 seconds, maybe 5 before the sound came back in one wave. By noon that day, the New York Times had pushed 4 separate alert notifications. The BBC broke into scheduled programming. Le Monde ran a front page with a single word above the fold. That word, in every language, in every time zone, was the same planet. But here is what the headlines couldn't fully communicate. What got lost in the rush of excitement? This discovery was not simply another exoplanet added to a list. At the time of the announcement, astronomers had confirmed more than 5,500 exoplanets orbiting stars beyond our solar system, 5,500 worlds, and this one was categorically different, not by degree, by nature. The nearest previously confirmed exoplanet to Earth with any claim to habitability was Proxima Centauri b, 4.24 light-years away, orbiting that temperamental red dwarf. The next closest candidates orbited stars dozens of light-years distant. Most confirmed exoplanets sit hundreds to thousands of light-years from Earth. At those distances, exploration is not a word that belongs in any serious engineering conversation. It is a word for philosophy lectures and science fiction novels. You cannot send a probe to something 800 light-years away and expect any human civilization to still be waiting for the data when it arrives. Alpha Centauri A, at 4.37 light-years, is different in a way that rewrites the entire conversation. If this planet were confirmed, how long do you think it would take humanity to actually send a spacecraft there? In 2016, a consortium of scientists and billionaires, including Stephen Hawking and Yuri Milner, announced Breakthrough Starshot, a proposal to build a fleet of gram-scale, laser-propelled probes, accelerated to 20% of the speed of light using a ground-based laser array. At 20% the speed of light, the travel time to Alpha Centauri is approximately 20 years. 20 years, within a single human lifetime. The proposal existed before this announcement as an elegant concept in search of a compelling destination. On August 14, 2025, it suddenly had an address. NASA convened an emergency internal review within 36 hours of the announcement. ESA called an extraordinary session of its Science Program Committee. JAXA and ISRO both issued formal statements within 48 hours acknowledging the discovery's implications for long-range mission planning. These were not publicity moves. These were institutions recalibrating their internal roadmaps because the fundamental premise of interstellar exploration, that we had no confirmed nearby target, had potentially just changed. The scientific community's reaction was more complicated. Many researchers responded with genuine, unguarded excitement, but a significant and vocal minority urged immediate caution. The peer review process was still running. The paper had cleared initial review, but not the full independent replication cycle that extraordinary claims demand. Several senior astronomers gave interviews pointing out, carefully and precisely, that a single detection without confirmation from an independent instrument is a candidate, not a confirmed planet. The distinction matters enormously in science, even when it makes for a less satisfying headline. None of that nuance made the front pages. What made the front pages was the image, the faint gold dot, the neighbor. For the first time in human history, the question of life beyond Earth was no longer a question about the infinite and unreachable cosmos. It was a question about the house 4 blocks down. The philosophical weight of that shift from abstract to addressable, from theoretical to potentially visitable, landed differently on different people. Religious leaders issued statements. Philosophers wrote overnight essays. Social media ran at a temperature it usually reserves for elections and disasters. And aerospace stocks, across every major exchange, climbed an average of 9% within 6 hours of the announcement. Because it turns out Wall Street becomes a true believer in science the moment science starts looking like infrastructure for future profit. Humanity had, for a few extraordinary weeks, something it had never quite possessed before, not just a hope, but a coordinate, a specific point in space, measurable, documented, peer-reviewed, attached to the nearest sun-like star, sitting at a distance that human engineering could theoretically reach, not in 10,000 years, in 20. But the naming discussions informal, playful, the kind that circulate on science forums and Twitter threads were just beginning in mid-October of 2025, when a second independent team pointed Webb at the exact same coordinates, and the screen showed nothing. Standard procedure. That's what the second observation was supposed to be. An independent team operating through the European Southern Observatory's allocated James Webb Space Telescope time. With a clear scientific mandate, point the telescope at the coordinates of the August detection. Collect data across the same infrared wavelength bands and begin the orbital parameter measurements that would allow a full characterization of the candidate planet's path around Alpha Centauri A. Confirmation, refinement, precision, the normal machinery of science, tightening its grip on a new discovery. They pointed Webb at the coordinates. They opened the same wavelength windows. And the signal was not there. Not faint, not degraded, not shifted slightly from the predicted position. Gone. The infrared emission that had survived 7 independent internal analyses. That had matched the spectral signature of a Saturn-class gas giant with extraordinary fidelity. That had anchored one of the most significant astronomical announcements in decades. It was simply absent from the data. The team widened their search radius, scanning a region several times larger than the original detection area, in case the planet's orbital motion had carried it farther from Alpha Centauri A than the models predicted. Nothing. They ran checks on every component of the instrument, the detectors, the coronagraph alignment, the pointing stability, the calibration frames. The telescope was performing perfectly. 3 consecutive nights of observation across different observing windows. 3 nights of the same result, a clean, empty field where something the size of Saturn was supposed to be sitting. Imagine you photograph a building today. It's there, solid, unambiguous, casting a shadow, reflecting light, every detail consistent with a real structure. 2 months later, you return to the same spot with a better camera, and the building is gone. No rubble, no foundation scar, no dust cloud still settling from a demolition. The lot is simply empty. as though the building was never there. That's the closest ordinary world analogy to what the ESO team was confronting. The first team, the Discovery team, responded immediately and without defensiveness. They released their complete raw data set, every calibration frame, every pipeline reduction step, every intermediate product to the full astronomical community within 72 hours of being notified of the non-detection. They invited independent reanalysis. They held an open video conference attended by more than 400 researchers across 6 continents, walking through every decision they had made during their 6 weeks of internal verification. No technical error was identified. No pipeline flaw was found. The raw data showed what the raw data showed, and no one examining it could identify a procedural reason for the original signal to be artifactual. What do you think actually happened? Did the planet vanish? Or was the original signal a mistake? The scientific community, which had spent August and September riding an unprecedented wave of collective excitement, pivoted into something rarer and more uncomfortable: collective bewilderment. Researchers who study exoplanets for a living, people with decades of experience characterizing planetary signals, ruling out false positives, understanding the full range of instrumental and astrophysical phenomena that can mimic or mask planetary detections, were openly stating that they did not have a clean explanation. That admission matters. These are not people given to public uncertainty. The normal rhythm of science involves confident claims, careful hedging, and measured language. What emerged in the weeks after the non-detection was something different, a genuine, shared acknowledgement that whatever had happened, it did not fit neatly into any established category. Planets do not disappear. That is not a controversial statement. It is a consequence of physics. A Saturn mass object does not dematerialize. It cannot cease emitting infrared radiation without a specific physical mechanism driving that change. It cannot relocate outside Webb's detection range in 8 weeks without leaving a trail in the orbital data. The two logical possibilities sitting at opposite ends of the problem were stark and uncomfortable. Either the planet was still there and something was preventing its detection, or the original signal had never been a planet at all. Neither option came with an easy explanation attached. What made this genuinely unprecedented in the modern era of exoplanet science was the specific combination of circumstances. This was not a transit detection that had failed to repeat transits have known false positive pathways. This was not a radial velocity signal that turned out to be stellar activity. Stellar mimics have well-documented spectral signatures. This was a direct infrared detection with a full spectral profile, confirmed internally 7 times, that subsequently produced a clean non-detection under what should have been identical observing conditions. There was no established template for this situation. In 8 weeks, the story had traveled from discovery of the century to mystery of the century, the fastest narrative reversal in the modern history of science communication. Journalists who had written breathless August pieces about humanity's new cosmic neighbor were now writing October pieces about the planet that played hide-and-seek with the most expensive telescope ever built. The tone shifted, the certainty evaporated, and in the space where a confirmed planet had briefly existed, something more unsettling moved in a question mark the size of a solar system. Astronomers had spent careers searching for planets that didn't want to be found, hidden behind stellar glare and instrumental limits. This was something else entirely. A planet that had apparently allowed itself to be found once, then actively refused a second look. The joke circulating in department common rooms was delivered with a tired kind of humor. Astronomers are used to planets hiding from them. This was the first time one seemed to be hiding on purpose. And from that moment, 4 separate groups of scientists on 4 different continents began building 4 completely different explanations for what had happened, each one internally coherent, each one grounded in real physics, and each one carrying a flaw at its center that the others were quick to find. The press conferences ended. The live streams went dark. The journalists filed their stories and moved on to the next crisis. What remained was a different kind of room entirely. Cold fluorescent light. Whiteboards covered in equations that hadn't been erased in weeks. Coffee cups stacked in towers of quiet desperation. No cameras, no moderators, no carefully worded public statements. Just scientists, some of the most rigorously trained minds on the planet, sitting with a data set that refused to make sense, trying to do the only thing their training had prepared them for, reason their way through the dark. The chaos of the non-detection had, by late October of 2025, begun to crystallize into something more structured. 4 distinct explanatory frameworks had emerged from the community's frantic weeks of analysis, each championed by a different group of researchers, each drawing on real physics, and each, when you looked closely enough, carrying a wound at its center that wouldn't close. Think of it less like a scientific debate and more like a detective investigation where every suspect has a credible alibi and an equally credible motive. The evidence is real, the crime is real, but the story keeps changing depending on who's doing the telling. Walk through it like a detective. That's the only honest way. Hypothesis 1. The original signal was a false positive. The detection in May and June of 2025 was never a planet. It was an artifact, a phantom produced by one of 2 mechanisms. Either a cosmic ray strike on JWST's infrared detectors, or a background celestial object that happened to drift into the observation field at exactly the wrong moment. Cosmic ray hits on space-based detectors are not exotic events. They happen constantly. High-energy particles, protons, heavier nuclei, the byproducts of supernovae and active galactic nuclei stream through the solar system continuously. And Webb's detectors are exposed to this environment every single second of every observation. When one of these particles strikes a detector pixel at the right angle with sufficient energy, it deposits charge that the readout electronics interpret as photons. A false bright spot? A ghost in the data. The Discovery team's pipeline included cosmic ray rejection algorithms, standard practice, built into every Sirius Space Telescope data reduction system. But no algorithm is perfect. Under certain conditions, a cosmic ray strike can mimic a faint compact source. The non-detection team, and several independent analysts who joined the public debate after the raw data release, pointed to this mechanism as at least plausible. The background object argument worked differently. Between Earth and Alpha Centauri, and far beyond Alpha Centauri A in the same line of sight, space is not empty. Distant galaxies, brown dwarfs, faint stellar remnants, any of these, if positioned precisely behind Alpha Centauri A and moving with their own proper motion, could appear briefly in a Webb observation window and then move out of frame by the time the second team looked. The positional overlap would be a coincidence, but coincidences exist. Statistics allow them. Would you trust a $10 billion instrument, or would you trust the mathematics of probability? The Discovery team rejected both variants of Hypothesis 1 with considerable force, and their reasoning was specific, not defensive. Cosmic ray artifacts have a known spectral signature. They are essentially featureless. A particle strike deposits charge across a pixel or small cluster of pixels in a way that produces a flat, structureless brightness spike. What the Discovery team had recorded was not flat. It had a complete molecular absorption spectrum, methane absorption bands at specific infrared wavelengths, ammonia features, a thermal profile consistent with a cold gas giant atmosphere. The probability that a random cosmic ray strike would accidentally produce a false signal with that precise spectral architecture, matching known planetary atmospheric physics at multiple independent wavelength positions simultaneously, was not zero, but it was extraordinarily small. smaller than the discovery team was willing to accept as an explanation without much stronger evidence. The background object argument faced a similar problem. A distant galaxy or brown dwarf would carry its own spectral fingerprint, one inconsistent with the atmospheric chemistry of a Saturn-class planet in a habitable zone. The spectrum that came back from the original detection didn't just look like a planet in general terms. It matched, at the level of individual molecular absorption features, what theoretical models predicted for a specific class of cool gas giant with a specific atmospheric composition. Like finding a footprint at a crime scene that doesn't just fit a shoe, it fits one specific shoe, in one specific size, with one specific wear pattern on the heel. That's when the comparison starts to feel uncomfortably precise. A perfect match, almost too perfect, argued the skeptics. Forensic investigators sometimes say that evidence which appears flawless deserves extra scrutiny precisely because of its perfection. Real signals are messy. Real detections come with noise, with minor inconsistencies, with the rough edges of physical reality. A signal that matches theoretical predictions almost exactly can occasionally mean you found something real, and occasionally it means the model that generated your expectations has contaminated your interpretation of your data. The raw data set went public. All of it. And what happened next was genuinely without precedent in the history of professional astronomy. Thousands of amateur astronomers on forums and collaborative platforms, equipped with downloaded copies of Webb's actual data and open-source reduction software, began running their own independent analyses. Most found what the professionals found. A handful found things the professionals had missed. Minor calibration inconsistencies in 2 of the 7 internal reanalysis runs, not large enough to explain the signal, but real enough to be noted. Several doctoral candidates at universities with no formal connection to either team published preprints within 3 weeks of the data release, identifying subtle pipeline choices that, if made differently, would have slightly altered the signal's measured brightness, though not its spectral shape, and not its statistical significance above the noise floor. It was the first time in history that the most expensive telescope ever built had its data crowdsourced in real time, and it produced both useful science and a level of public engagement with actual astronomical data that no outreach program had ever achieved by design. Hypothesis 1 was alive, battered, contested, rejected by the discovery team, partially supported by the skeptics, unresolved by the public data analysis, alive. But if the false positive hypothesis is wrong, then there is a possibility even stranger: the planet is still there. It is simply hiding behind its own star. And the mathematical probability of that happening in exactly this window of time will make you question everything you thought you knew about orbital mechanics. So, a planet appeared, then it vanished. Hypothesis 1, false positive, cosmic ray artifact. Background interloper has real arguments behind it, but it cannot cleanly explain away a spectral fingerprint that matched planetary atmospheric chemistry at multiple independent molecular absorption features simultaneously. The discovery team's raw data survived public scrutiny. The wound in Hypothesis 1 is real, and it doesn't close, which brings us to Hypothesis 2. And this one, at first glance, feels like solid ground. The planet didn't disappear, it's still there. It simply moved behind Alpha Centauri A, hidden from Webb's line of sight by the star itself. In orbital mechanics, this event has a name: stellar occultation. A planet passes behind its host star. The star's disk blocks the planet's thermal emission, and from our observing position, the planet becomes undetectable for the duration of that passage. It's a completely ordinary phenomenon. It happens in our own solar system. It has been observed in exoplanet systems hundreds of times. There is nothing exotic or physically suspect about it. The physics is routine. The problem is the timing. To understand why the timing is the issue, you need to think about what 8 weeks means for a planet orbiting in a habitable zone. A planet at habitable zone distances around a star like Alpha Centauri A, which is almost identical in mass and luminosity to our Sun, would orbit at roughly the same distance as Earth orbits the Sun, approximately 1 astronomical unit. At that distance, one complete orbit takes approximately 1 year, 365 days, for that planet to be behind the star, fully occulted, completely shielded from Webb's view during the precise 8-week window between the May through June discovery observations and the October confirmation attempt. The orbital geometry would have to align in a very specific way. The researchers who ran the probability calculations came back with a number less than 2.3%. Let that sit for a moment. Less than 2.3% chance that the planet happened to slide behind its star in exactly the window between 2 observations, not before, not after, but precisely during those 8 weeks out of a full year-long orbital cycle. Would you bet on 2.3% odds, knowing that if you're right, you just found the nearest extrasolar planet ever confirmed? Think of it this way. Flipping a fair coin and getting heads 6 times in a row, that's about 1.6% probability, lower than 2.3%. But the same neighborhood, it can happen. Anyone who has ever flipped a coin knows it can happen. But if you flipped 6 heads in a row in a casino where the stakes were the credibility of an entire scientific announcement, you would look at the coin very carefully before accepting the result. You wouldn't call it impossible. You'd call it suspicious enough to demand a closer examination. The group that built the case for Hypothesis 2 understood this. They weren't pretending the odds were comfortable. Their argument was more pragmatic. Low probability is not zero probability, and the correct response to a 2.3% event is not to rule it out. It's to design an observation that can test it directly. And that is exactly what they did. If the planet is on a roughly year-long orbit around Alpha Centauri A, and it moved behind the star in late September or early October of 2025, then working backward and forward from that assumption gives you a predicted orbital arc. From that arc, you can calculate when the planet should emerge from behind the star and become detectable again. The math pointed toward a return window in the first quarter of 2026, which became the primary scientific justification for the emergency scheduling of a 3rd observation campaign, the most resource-intensive Webb allocation ever granted on an expedited timeline. There was logic to the plan. Real, defensible logic. If the planet reappears at the predicted time, in the predicted location, consistent with the calculated orbital parameters, then Hypothesis 2 is confirmed. The discovery stands, and the 2.3% event gets added to the long list of improbable things that nevertheless happened. But then came the fatal wound. If the planet has a real orbital period, a consistent, calculable path around Alpha Centauri A, then the original May through June detection should have contained evidence of that motion. Specifically, it should have shown a Doppler shift. As the planet moves along its orbit, its velocity relative to Earth produces a measurable shift in the wavelengths of its spectral features. A planet moving toward us in its orbit compresses those wavelengths, slightly blue shift, moving away. It stretches them. Redshift. The magnitude of this shift, combined with the spectral line's positions, allows astronomers to calculate orbital velocity and, from orbital velocity, orbital period. The original detection showed no measurable Doppler shift, none that could be extracted from the data with statistical confidence. This could mean several things. The planet might have been near the point in its orbit where its motion was predominantly perpendicular to our line of sight, the point at which Doppler shift is minimal, sometimes called the stationary point of an orbit. If the May through June observations happen to catch the planet at exactly that orbital phase, the absence of detectable Doppler shift would be consistent with hypothesis 2. But, and this is the part that made the orbital mechanics camp genuinely uncomfortable, catching a planet at its stationary point and having it move behind the star within the same 8-week window compounds the coincidence problem considerably. Now you're not asking for one improbable alignment, you're asking for two. Two camps formed, and their disagreement was unresolvable without the third observation. The first camp held that low probability arguments are philosophically dangerous in science, that the history of astronomy is full of events that seemed statistically improbable until they were understood, and that dismissing a physically plausible mechanism because of a 2.3% threshold is not rigor, it's overcaution. The universe does not guarantee that interesting things happen at convenient statistical frequencies. The second camp countered that science cannot operate as a collection of low probability explanations stacked on top of each other. One improbable coincidence can be accepted. Two simultaneously orbital phase alignment plus occultation timing starts to resemble special pleading dressed in mathematical language. Science doesn't build on luck, it builds on mechanisms. Astrophysicists were in public disagreement about a 2.3% probability, parsing it, arguing it, publishing preprints about it with the intensity usually reserved for questions about the fundamental constants of nature. Meanwhile, somewhere outside the physics department building, people who buy lottery tickets every week at odds roughly 100 times worse were presumably watching this debate with a certain quiet sympathy. But if both hypotheses carry wounds that won't heal, the third one will make you exhale with relief. And then immediately take that breath back, for a reason nobody saw coming. Hypothesis 3 was the one the public loved. Not loved in the way people love a solution. Loved in the way people love a disaster, with a kind of horrified fascination that makes it impossible to look away. A catastrophic collision, a planet-destroying impact, a violence so total, so complete, that it erased a Saturn-mass world from existence in the span of 8 weeks. Dramatic, final, the kind of event that writes itself into a screenplay without needing a second draft. And the hypothesis had genuine precedent behind it. The solar system's own history is written in collision scars. The asteroid belt between Mars and Jupiter is, in one interpretation, the remains of a planet that never fully formed because Jupiter's gravitational interference prevented accretion, a world that was stillborn in fragments rather than killed in impact. The late heavy bombardment, approximately 3.9 billion years ago, was a period of intense asteroid and comet impacts across the inner solar system that reshaped planetary surfaces wholesale. Earth's own moon, the leading model tells us, formed when a Mars-sized body struck the early Earth with enough energy to vaporize portions of both objects, ejecting the debris that eventually coalesced into the moon we see today. Planetary scale violence is not hypothetical. It is the documented background condition of solar system formation and early evolution. So the question the Hypothesis 3 camp was asking was not unreasonable on its face. What if the planet detected in May of 2025 was struck by something enormous, a rogue body, an uncharted giant impactor with enough energy to shatter it? What if the signal vanished in October because the planet no longer existed in any coherent form? To understand why this is compelling, you have to appreciate the scale of energy involved in a planet-destroying collision. A Saturn-mass object contains roughly 95 times the mass of Earth. Destroying it, not just disrupting it, but converting it into dispersed debris, requires energy on a scale that dwarfs anything in human experience by many orders of magnitude. The impact that created Earth's moon released energy equivalent to roughly 100 million nuclear weapons detonating simultaneously. A collision capable of destroying a Saturn-class planet would release energy orders of magnitude beyond that. It would be, by any measure, one of the most energetic events in the observable universe within that time period. If the planet still exists, but cannot be seen, what do you think is hiding it? And that energy doesn't vanish quietly. It converts into heat, into radiation, into expanding clouds of vaporized and fragmented material. The debris field from a planetary collision of that magnitude would glow intensely in infrared wavelengths for years, potentially centuries after the impact. The fine silicate dust thrown into orbital paths around Alpha Centauri A would produce a characteristic emission spectrum, bright and unmistakable to an infrared telescope of Webb's sensitivity. Hot, rapidly expanding gaseous ejecta would produce emission lines specific spectral signatures of ionized and excited atoms that no pipeline artifact or calibration error could mimic. The hypothesis. 3 researchers had one advantage over every other camp. Their prediction was testable immediately, with data that already existed. Webb's October 2025 observations, the same data that showed no planet, were also sensitive to precisely the signatures a planetary collision would have produced. The non-detection team went back through their dataset, looking not for the planet, but for its hypothetical aftermath. Excess infrared continuum emission from hot debris, silicate dust features at 10 micrometers and 18 micrometers wavelength, the characteristic glow of pulverized rock, emission lines from shocked gas, any thermal anomaly in the region where the planet had been detected 4 months earlier. They found nothing. Clean sky. No excess emission of any kind above the background noise floor. Not a whisper of debris. Not a trace of the thermal afterglow that a collision energetic enough to destroy a Saturn-mass planet would have left burning in that region of space for decades. Think of it this way. Imagine a thermonuclear weapon detonated in the middle of a city, and then, 8 weeks later, someone photographs the same location and finds not rubble, not radiation, not a crater, not so much as a scorch mark, just empty ground, as though nothing happened. That's the physical equivalent of what the absence of debris result means for hypothesis 3. A weapon that leaves no trace is not a weapon that fired. A collision that leaves no debris is not a collision that occurred. This is where hypothesis 3 separates itself from every other explanation on the table. The false positive argument can't be definitively disproven by the data alone. It's an epistemological question about signal interpretation. The orbital occultation argument can't be ruled out without the third observation. But hypothesis 3 makes a specific, concrete, immediately testable prediction about what the October data should contain, and the October data contains none of it. Hypothesis 3 is the only explanation that was not merely weakened by existing evidence. It was eliminated by it. This matters more than it might initially seem. The process of scientific reasoning is not just about finding the right answer. It's about collapsing the space of possible answers by eliminating the ones that contradict observation. Every eliminated hypothesis is progress, even when it feels like a dead end. Knowing the planet was not destroyed is not a small thing. It means the planet, in some physical form, must still exist somewhere in that system. Destroyed planets leave evidence. This one left nothing, which produces a new paradox, harder than any of the individual hypotheses. The planet was not a false positive. The spectral data is too specific. It was not behind its star. The timing odds and missing Doppler shift strain credibility. It was not destroyed. The clean October data is unambiguous. So what, exactly, is a Saturn-mass planet doing while 3 of the world's leading explanatory frameworks fail to account for its behavior? It is, apparently, becoming invisible on its own terms. The collision hypothesis died quietly in the data, which was genuinely good news for the planet, and genuinely terrible news for the half-dozen film production companies that had already reached out to the Discovery Team's institution about documentary rights. Hollywood had its catastrophe narrative ready. The universe declined to cooperate, and now we arrive at the strangest hypothesis of all, the one where a gas giant the size of Saturn suddenly transforms itself so completely that it becomes invisible to the most powerful technology humanity has ever built. Hypothesis 4 came in 2 flavors. Both were strange. One was physically possible, but observationally unprecedented. The other was physically possible, but so extreme in its requirements that calling it a long shot would be generous. Together, they represented the last coherent framework left standing after the collision hypothesis had been eliminated by the data, and the best argument any of the 4 camps could muster for why a Saturn-mass planet might vanish from Webb's infrared vision without being destroyed, without being hidden by its star, and without being a false detection in the first place. The first variant, the planet passed through a dense interstellar dust belt, not the thin, diffuse interplanetary medium that permeates all stellar systems, something substantially thicker. A localized concentration of micrometer-scale silicate and carbon particles, orbiting Alpha Centauri A in a ring or cloud configuration, positioned such that the planet's orbital path carried it directly through the densest region during the 8 weeks between observations. As the planet moved into that dust concentration, the particles would have enveloped it like a shroud, absorbing its outgoing infrared thermal emission before it could reach Webb's detectors across 4.37 light-years of space. The physical mechanism is real. Dust absorbs infrared radiation efficiently. The particle sizes most effective at blocking mid-infrared wavelengths, roughly 1 to 10 micrometers in diameter, are exactly the sizes produced by collisional grinding of rocky material in planetary systems. In principle, a sufficiently dense dust belt could act as a thermal cloak. Think of it like putting on an insulated jacket in a room monitored by a thermal imaging camera. Your body heat is still being produced, but the insulation intercepts it before it reaches the camera's sensor. And on the screen, you simply vanish, body temperature unchanged, radiation blocked, invisible. The problem arrived the moment anyone looked at Alpha Centauri A's observational history. This system had been studied for decades before Webb arrived. Ground-based infrared surveys, Spitzer observations, Herschel Space Observatory data. All of it pointed to the same conclusion: Alpha Centauri A is an exceptionally clean system. The ratio of infrared excess above the stellar photosphere, the standard diagnostic for the presence of warm dust, was consistent with essentially zero debris disk emission. No thick dust belt had been detected at any wavelength, in any prior observation, by any instrument. The system's infrared cleanliness was, if anything, one of the features that had made it an attractive target for planet searches, because heavy dust contamination complicates planetary signal extraction. For Hypothesis 4's first variant to work, a dust belt dense enough to completely extinguish a Saturn-class planet's thermal signature would need to exist in a system where no prior observation had ever hinted at significant dust. It would have to be dense enough to absorb the planet's emission across all relevant infrared wavelengths, not just one band, but the full spectral range Webb had probed, while simultaneously being thin enough that Webb's own direct imaging of the region showed no excess emission attributable to the dust itself. A curtain that hides a planet but leaves no shadow of its own. The physics permits it. Technically, the prior data made it extraordinarily difficult to believe. The second variant was stranger still. What if the planet itself changed? Not its position, not its environment, its own atmosphere. A rapid, extreme transformation of atmospheric composition. So severe that the gases responsible for the original infrared spectral signature were replaced by something else something that absorbs rather than emits at the wavelengths Webb was measuring, or that redistributes the planet's thermal emission into wavelength ranges Webb was not observing in the October campaign. Of all four hypotheses at this point, which one strikes you as the most plausible? For context on how unprecedented this would be, Jupiter's atmosphere has been continuously observed for centuries. Its cloud bands shift, its Great Red Spot has contracted measurably over decades. Its chemical composition shows subtle variations tied to seasonal and orbital dynamics. But the fundamental infrared character of Jupiter, the thermal emission profile that any telescope would see from outside the solar system, has not changed in any dramatic way on timescales shorter than years, let alone weeks. Saturn is the same. Every gas giant in our solar system, and every one of the dozens of hot Jupiters and warm Neptunes characterized by infrared spectroscopy in other star systems, displays an infrared signature that is either stable or evolves slowly on timescales of years to decades, driven by gradual chemical and thermal processes. An atmospheric transformation, complete enough to render a Saturn-mass planet invisible to Webb's infrared instruments in 8 weeks, would require a physical process operating at a speed for which no theoretical model in the entire literature of planetary science had ever been constructed. It wasn't just unprecedented observationally, it was unprecedented theoretically. No one had even bothered to write down the equations for it, because no observation had ever demanded it. The shared wound running through both variants of Hypothesis 4 was the same coincidence of scale. Each mechanism required a very specific set of conditions. The dust belt, perfectly placed, the atmospheric chemistry, transformed at impossible speed, converging in the exact 8-week window that happened to fall between observations, not years before, when no telescope was watching, not months later, after confirmation could have been achieved. In the 8 weeks between a discovery and its attempted replication, the timing wasn't just improbable. It had the uncomfortable quality of precision that makes scientists look at each other across conference tables without saying what they're actually thinking. And yet, and this is the part that kept the Hypothesis 4 camp alive and working, if either mechanism were real, the scientific implications would exceed even the original discovery in importance. A previously unknown class of dense, localized dust structure inside a mature stellar system with no detectable debris disk would overturn models of disk evolution that had taken 30 years to build. A physical process capable of transforming the infrared emitting chemistry of a gas giant's atmosphere on a timescale of weeks would be the most dramatic planetary science discovery since the first hot Jupiter upended theories of solar system formation in 1995. The mystery, if Hypothesis 4 was right, would be worth more to science than a simple confirmed planet. 4 hypotheses, then 4 research groups, 4 sets of arguments, 4 different predictions about what the next observation would show, each one grounded in legitimate physics, each one carrying a flaw it couldn't fully account for. 4 world-class scientific teams collectively representing some of the deepest expertise in observational astronomy, planetary science, and stellar astrophysics, and every one of them wrong in a different direction. That's not a crisis. It would be easy to read it as one, but it isn't. It is precisely what science looks like when it reaches the edge of what its current tools can resolve when the data is real, but the interpretation space is larger than the evidence can yet constrain. 4 wrong hypotheses pointing toward one unknown truth is not failure. It's the most honest map of a territory that hasn't been fully explored yet. The 4 hypotheses from the world's leading scientists were all flawed in different ways. None of them quite fit. That isn't a collapse of the scientific method. It's the scientific method operating exactly as designed, refusing to accept a comfortable answer when the evidence doesn't fully support one. Then, at the close of 2025, JWST executed its third observation of Alpha Centauri, the highest resolution campaign ever applied to this system, and the data that came back resolved none of the 4 hypotheses. It made everything incomparably more complicated. The third observation campaign was the most carefully engineered scientific undertaking in the history of Alpha Centauri research, which, given what the previous 2 attempts had produced, was either a testament to human determination or a definition of stubbornness, depending on who you asked. Planning began in November of 2025, immediately after the 4 hypothesis deadlock had become obvious to the community. Multiple independent teams were brought into the observation design process simultaneously, not sequentially, as is typical, but in parallel, so that no single group's theoretical assumptions could unconsciously shape the data collection strategy. The wavelength coverage was expanded beyond the original May through June campaign. The time resolution. How frequently the detector sampled incoming photons was increased to its maximum practical rate for this type of target. 3 separate analysis pipelines, developed by 3 teams with no cross-communication during the reduction process, would process the raw data independently before any comparison was attempted. Every possible procedural bias that could have influenced either the original detection or the October non-detection was identified and guarded against. The data began arriving in late December of 2025 and continued into the first weeks of 2026. The infrared signal returned at the predicted coordinates, in the expected wavelength bands. The point source was back faint but real, above the noise floor, spectrally consistent with the original detection's atmospheric fingerprint. The first team to complete their independent pipeline reduction sent a single message to the coordinating committee: "It's there." The second team confirmed within 6 hours. The third, 12 hours after that. For approximately 36 hours, there was a cautious, exhausted relief circulating through the group's communication channels. The planet had come back. Maybe the orbital occultation explanation was right. Maybe the 2.3% event had simply happened. The third observation would provide the orbital arc data needed to confirm it. Everything could still resolve cleanly. Then someone looked more carefully at the time series data. The signal was not behaving like a planet. Every gas giant ever observed in our solar system, in the hundreds of exoplanet systems characterized by infrared photometry, produces a thermal emission signal that is either constant or varies in slow, predictable ways tied to orbital phase, atmospheric circulation patterns, or stellar irradiation geometry. The variation timescales are long. Jupiter's thermal output, integrated across its disk, fluctuates by less than 1% on timescales shorter than days. The hot Jupiters detected around other stars show infrared brightness variations tied to their synchronous rotation and day-night temperature contrasts, but those variations are smooth, sinusoidal, and repeat on periods of hours to days in a perfectly regular rhythm. What the third campaign's time series data showed was none of that. The signal was flickering, irregular, non-periodic fluctuations in infrared brightness, brightest at some moments, dimming significantly at others, then returning, then dropping again, with no repeating pattern that any of the 3 analysis teams could extract from the data. The fluctuation timescale ranged from as short as 40 minutes to as long as 6 hours. The amplitude of the variations, how much brighter or dimmer the signal swung, was large enough to be unambiguous above the noise. Not a marginal effect requiring statistical arguments to defend. Imagine a lighthouse on a coast. You expect it to rotate at a fixed speed, sweeping its beam in a reliable, predictable rhythm. Instead, what you see is a light that pulses brightly, then dims to almost nothing, then surges, then flickers with no discernible pattern. Not a malfunction rhythm, not random noise, but something in between, structured enough to feel intentional. irregular enough to resist any decoding. The beam is too complex to be instrument failure, but it matches no chart, no known signal type, no established pattern from any lighthouse in any database. That's the closest everyday analogy to what the third campaign's time series produced. Do you know of any other astronomical phenomenon that produces an irregularly flickering infrared signal like this? The three analysis teams spent 2 weeks comparing their independent reductions before releasing anything publicly. They were looking for a pipeline artifact that could explain the flickering, an instrumental systematic, a calibration residual, a known detector behavior under certain thermal conditions. They found nothing. The flickering was in the data from all three reductions. It was real. 3 new explanatory scenarios emerged from the team's internal discussions, each attempting to account for the irregular variability. None of them were given formal names in any publication. The researchers themselves referred to them informally, carefully, with the language of people who understood that putting certain ideas in writing without more supporting evidence was a professional risk. The scientific culture around extraordinary claims operates with a conservatism that sometimes frustrates outsiders, but exists for reasons earned through decades of retractions and reproducibility failures. The preprint went to arXiv on a Tuesday morning in late January of 2026. By Thursday, it had been downloaded 400,000 times, the largest 2-day download count in the platform's history, surpassing even the original LIGO gravitational wave detection paper from 2016. 400,000 times in 48 hours. Physicists, astronomers, planetary scientists, atmospheric chemists, and a very large number of people with no formal scientific background at all, reading the same document, looking at the same light curves, trying to understand what a planet was doing. The astronomical community's reaction was not the excited confusion of the post-discovery weeks. It was something quieter and more unsettled. Researchers who had been publicly committed to one of the 4 hypotheses went silent on social media. Several withdrew preprints they had been circulating. The irregular variability was not something any of the 4 existing frameworks had predicted. A false positive doesn't flicker, it either exists or it doesn't. An occulted planet behind its star produces no signal at all, not a variable one. A destroyed planet leaves debris, not a fluctuating thermal source. A dust-cloaked or atmosphere-transformed planet, even under the most exotic variants of Hypothesis 4, would be expected to produce a steady, suppressed signal. Not this erratic, surging, dimming, surging rhythm. The only class of astronomical objects known to produce irregular, non-periodic flickering signals on timescales of minutes to hours in the relevant energy ranges were neutron stars and pulsars, the collapsed, hyperdense remnants of massive stellar explosions, objects made of matter so compressed that a teaspoon would weigh billions of tons, spinning dozens to hundreds of times per second and emitting radiation in lighthouse-like beams. They produce the kind of irregular variability the Alpha Centauri signal showed, for reasons rooted in the extreme physics of degenerate matter and intense magnetic fields. Alpha Centauri A is not a neutron star. The object at its coordinate is not a pulsar. The comparison was not a hypothesis. It was an anomaly report. A way of saying, the only things we know that behave this way are things that are nothing like what this is supposed to be. The informal name the team started using in their internal meetings was the blinker. Not in any paper, not in any formal communication, just in Slack threads and video calls when they needed something to call it that wouldn't trigger a media interpretation crisis if someone's screen was accidentally shared. They needed a word. That was the word. And this is the moment the story outgrew every single hypothesis that had been proposed to contain it. Because when you lay all 3 observation campaigns side by side and look at the complete picture, a question larger than any individual explanation begins to take shape. Do we actually know what we were looking for? Before moving forward, stop. Not because the story is over, because this is exactly the moment where the temptation to rush toward resolution is most dangerous, both for scientists working the problem and for anyone trying to understand what the Alpha Centauri episode actually means. The blinker is real data. The 4 failed hypotheses are real science. The bewilderment is genuine. But bewilderment is not the same as failure. And understanding the difference between the two is the only way to make sense of everything that comes next. So take a breath. Look at where we are and ask the honest question, is this a crisis? Or is this exactly what science is supposed to look like when it reaches the edge of what it currently knows? The history of astronomy offers a useful answer, and it is not a comfortable one. In 1903, a French physicist named René Blondelot announced the discovery of a new form of radiation he called N-rays, named after Nancy, the city where he worked. Dozens of other researchers across Europe quickly confirmed his findings. They saw the N-rays too, measured their properties, published papers. The effect was replicated in multiple laboratories by multiple investigators operating in good faith. Then an American physicist named Robert Wood visited Blondelot's laboratory, quietly removed a critical prism from the experimental apparatus without telling anyone, and found that the researchers continued to report seeing N-rays that the apparatus could no longer physically produce. The N-rays had never existed. They were a collective hallucination born from unconscious expectation, researchers seeing what the field's social pressure told them to see. Then there was Vulcan. For decades in the 19th century, astronomers searched for a planet orbiting between Mercury and the Sun, predicted by Urbain Le Verrier, to explain small irregularities in Mercury's orbit. Multiple observers reported sightings. The planet was given a name. It appeared on some star charts. It did not exist. The irregularities in Mercury's orbit were eventually explained by general relativity, which no one in Le Verrier's time had the conceptual framework to imagine. The instrument wasn't broken. The observers weren't dishonest. The framework was simply incomplete, and the gap between reality and the available theory was filled, temporarily, by a phantom. These are the astronomical equivalents of the Piltdown Man constructed answers to questions that the available evidence couldn't yet honestly answer. They are not embarrassments unique to a less rigorous era. They are warnings that remain relevant as long as human beings are doing the observing and interpreting. Do you think science should publish a discovery before full confirmation, or stay silent until certainty is absolute? The Alpha Centauri episode from 2025 through 2026 sits inside this history, not outside it. And the specific psychological pressure it generated was unusual because it ran in 2 directions simultaneously. Before the October non-detection, the pressure was toward belief. The world wanted a planet around Alpha Centauri A. The public wanted it. The media wanted it. The space agencies wanted it. And being honest, many of the scientists involved wanted it too. That kind of collective desire doesn't override rigorous methodology in any overt way. It operates at the margins, in the choice between 2 equally plausible interpretations of an ambiguous data point. The one that supports the exciting result gets fractionally more weight. In the decision about whether a signal is above the detection threshold, the threshold gets evaluated with fractionally more generosity. No one lies. No one fabricates. But the invisible hand of confirmation bias, the documented, well-understood, cognitive tendency to weight evidence that confirms existing expectations more heavily than evidence that challenges them, is always present, always pushing. After the non-detection became public, the pressure inverted. Now the world wanted the original signal to be wrong. Reputations were at stake. Institutions were embarrassed. The narrative had shifted from triumph to controversy. And the social reward structure suddenly favored skepticism over credulity. Researchers who had been cautious about the original announcement now had every incentive to find the flaw. to be the person who identified the error and restored scientific order. That pressure toward debunking, toward delegitimizing the original result, is equally capable of distorting analysis in the opposite direction. A non-detection that might have been investigated more carefully gets accepted as definitive. A potential instrumental explanation for the October null result gets examined less rigorously than it deserves, because the conclusion it would support is the inconvenient one. Both pressures were real. Both were operating simultaneously on a community trying to evaluate some of the most consequential astronomical data ever collected. This is not a scandal. It is a description of how human cognition interacts with high-stakes scientific investigation, and recognizing it is the first step toward designing processes that mitigate it. Which brings us to the machine itself. JWST was not built with Alpha Centauri as its primary target. Its coronagraph systems, its detector configurations, its observation planning tools, all of them were optimized for a range of scientific objectives, and nearby bright binary stars were not high on that list. The proximity that makes Alpha Centauri A scientifically compelling, 4.37 light-years, practically next door, creates an observational geometry that JWST was not specifically designed to handle cleanly. The two stars of the Alpha Centauri AB binary are bright enough and close enough together on the sky that suppressing their combined glare to the level required for sensitive planet detection pushes Webb's coronagraphic performance to its operational limits in ways that had not been fully characterized before the 2025 campaign. Think of the electron microscope, among the most powerful imaging tools ever constructed, capable of resolving individual atoms, revealing the internal structure of viruses, mapping the surface topology of materials at scales the naked eye cannot conceive of. But there is a minimum working distance. Below a certain range, the electron beam itself disturbs the sample. The focal geometry breaks down, and the image degrades rather than improving. The instrument is not weak. The problem is that certain targets fall inside the zone where the instrument's own operating principles become the limiting factor. Alpha Centauri sits inside JWST's equivalent of that zone. Not so close that observation is impossible, as the three campaigns demonstrated. Real data can be collected, but close enough that the systematic uncertainties in the data, the residual stellar speckle noise, the coronagraph leak patterns, the detector saturation effects near the star's position, are large enough to complicate interpretation of signals at the brightness levels expected from planetary companions. The telescope is not inadequate. The challenge is genuinely unique. This is precisely why the next generation of instruments matters so directly. The extremely large telescope, currently under construction in the Atacama Desert in Chile, with a primary mirror 39 meters in diameter, will achieve angular resolution and contrast performance that specifically address the observational geometry of nearby bright stellar systems. LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, was in its design study phase, explicitly incorporating Alpha Centauri as a benchmark target, the system against which the required coronagraphic contrast was evaluated. HabEx, another proposed large space telescope concept, similarly identified Alpha Centauri A as among the highest priority targets for direct imaging of potentially habitable planets. These instruments are not being built in response to the 2025 discovery, but the episode gave their scientific case a concreteness and urgency that no abstract proposal had previously achieved. The contradictions in the data are not the story ending badly. They are the story doing what stories about the boundary of knowledge always do, revealing that the boundary exists, marking where it runs, and defining exactly what needs to be built to push past it. A $10 billion space telescope is struggling with a neighbor 4 light-years away, while simultaneously imaging galaxies formed when the universe was less than 1 billion years old, structures 13 billion light-years distant, seen with extraordinary clarity. The universe arranged its nearest interesting neighbor in exactly the spot most awkward for the instrument best suited to study it. If the cosmos has a sense of humor, it's a very specific, very technical one. But the story isn't finished, because while 4 teams of scientists were arguing about 4 hypotheses, a 5th group was doing something entirely different. They weren't looking for the planet. They were looking for why we couldn't find it. The Alpha Centauri episode of 2025 through 2026 was not a failure. Say that plainly, because the instinct to read it as one is strong and understandable. A discovery announced to the world. A planet that vanished. 4 hypotheses that couldn't hold together. A 3rd observation producing data. Stranger than the absence it was meant to explain. By the standards of how science gets reported, clean breakthroughs, linear progress, heroes with answers, this looks like a mess. But by the standards of how science actually functions at the boundary of what is known, it is something close to a perfect example. Consider what happened with X-rays. When Wilhelm Röntgen published his discovery in 1895, the initial data was so anomalous, radiation passing through solid matter, casting shadows of bones inside living flesh, that several prominent physicists dismissed it as instrument error. The Royal Society of Medicine treated the first clinical X-ray images with institutional skepticism. The data contradicted established understanding of electromagnetic radiation so thoroughly that contradiction itself was taken as evidence against the result. Röntgen was not vindicated by a single clean confirmation. He was vindicated by a slow accumulation of replications, each one chipping away at the space of possible alternative explanations until no alternative remained. Or consider LIGO, the Gravitational Wave Observatory, in September of 2015. When the detectors in Louisiana and Washington State simultaneously registered a signal consistent with 2 black holes merging 1.3 billion light-years away, the team sat on the data for 5 months before announcing anything publicly. 5 months. Not because they doubted the signal they were fairly certain within weeks, but because extraordinary claims demand extraordinary verification. And the peer review process for that announcement involved hundreds of researchers checking every possible instrumental artifact, every conceivable source of correlated noise between the 2 detectors, every potential systematic error in the pipeline. The discovery was real. The caution was also real. Both things were necessary. The Rosalind Franklin story, embedded in the DNA double helix discovery, showed something different, but equally important, that contradictory data from multiple investigators working with different methods and different assumptions can coexist for years before resolving into clarity. Franklin's X-ray crystallography data, Watson and Crick's model building, Chargaff's base pairing ratios, 3 separate lines of evidence, each incomplete on its own, converging on a structure that none of them could have reached alone. The contradictions were not obstacles to the discovery. They were the discovery's scaffolding. Peer review and replication are not bureaucratic obstacles to scientific progress. They are its immune system. They exist precisely because human beings are pattern-seeking, expectation-confirming, socially influenced observers who need structured external pressure to catch what their own cognition naturally obscures. The Alpha Centauri data went through that immune system and emerged neither confirmed nor refuted, which is exactly the correct outcome when the evidence genuinely doesn't yet support a definitive conclusion. The 3rd observation's contradictory data did not end the research program. It generated 12 independent papers in 3 months, 12 separate groups, 12 different methodological approaches, 12 sets of conclusions that overlapped, contradicted, and refined each other in the way that scientific literature is actually supposed to work. Not a single authoritative voice from the top. A distributed, sometimes cacophonous, ultimately self-correcting conversation happening simultaneously across institutions on 4 continents. Which future telescope do you think will finally deliver the definitive answer about Alpha Centauri's planets? The open data policy that JWST's operating consortium maintained throughout the episode, releasing raw data sets publicly, making calibration files accessible, publishing pipeline documentation, allowed something unprecedented to happen at scale. Thousands of amateur astronomers, citizen scientists with downloaded reduction software and consumer-grade computing hardware, worked through the same data as the professional teams. Most found what the professionals found. Some found things the professionals had missed. Minor calibration inconsistencies in 2 of the 7 original internal analyses. A possible systematic in the coronagraph speckle pattern that the formal pipeline had not fully accounted for. These contributions did not resolve the mystery, but they narrowed it, and they were made possible entirely by the decision to treat the data as a public resource rather than an institutional asset. The unexpected return buried in the reanalysis of the Alpha Centauri field data, the extended background region surrounding the target, that most researchers treat as noise to be subtracted. 3 previously uncatalogued objects were identified. A faint galaxy at an estimated redshift, placing it roughly 2 billion light-years distant. A cold brown dwarf candidate with a spectral type suggesting a surface temperature near 700 Kelvin, and an unclassified infrared source whose nature remained genuinely ambiguous in the first pass analysis. None of them were related to the Alpha Centauri planet mystery. All of them were new to science. The search for one thing produced, incidentally, 3 others. That is how knowledge compounds at the frontier. By early 2026, the episode had been formally incorporated as a case study into graduate astrophysics curricula at MIT, Caltech, and the European Southern Observatory's graduate training program in Garching. Not as an example of failure, as an example of the full complexity of high-stakes observational science, the cognitive pressures, the instrumental limits, the peer review dynamics, the public communication challenges, and above all, the epistemic discipline required to say, "We don't know yet," when the evidence genuinely supports no other honest conclusion. There is a psychology to scientific uncertainty that runs counter to how most people experience motivation. Most of us find clarity energizing and ambiguity draining. Scientists who have spent careers at the research frontier report the opposite, that a clean, settled answer closes a door, while an unresolved anomaly holds one open. The blinker, the vanishing planet, the 4 wounded hypotheses. These are not dead ends. They are open doors with unknown rooms behind them. And open doors, in research, attract more human energy than closed ones. 12 independent papers from a planet that may not exist, outpacing the publication rate of most confirmed exoplanet systems in the same period. That is, by any measure, the strangest and most productive ghost in the history of astronomy. And from this mystery, 3 future telescope programs were fundamentally reshaped, because Alpha Centauri turned out to be not just an observation target, it became the benchmark against which we measure our own limits. 3 generations of observational infrastructure are currently in motion simultaneously under construction, under design review, or moving through funding authorization, and the Alpha Centauri episode accelerated the momentum behind all of them in ways that budget documents and mission proposals from 2024 had not anticipated. The most immediate is the extremely large telescope, rising from the rock of Cerro Armazones in the Atacama Desert of Chile. Its primary mirror is 39 meters in diameter. To put that in physical terms, the entire light collecting area of the Hubble Space Telescope's mirror could fit inside one of the ELT's individual mirror segments, with room to spare. Its first light is projected for 2028, pending construction milestones, and at near-infrared wavelengths, precisely the range relevant to detecting planetary thermal emission around nearby stars. The ELT will achieve angular resolution 16 times finer than JWST, not 16% better, 16 times. An entirely different resolving capability, applied to the same class of targets that Webb struggled to separate cleanly from their host star's overwhelming glare. The ELT's high-contrast imaging instrument, designated MIDIS, the mid-infrared ELT imager and spectrograph, was designed in part with exactly Alpha Centauri-type targets in mind. Ground-based telescopes face atmospheric turbulence that space observatories avoid. But extreme adaptive optic systems, mirrors that flex thousands of times per second to compensate for atmospheric distortion, have advanced to the point where ELT's effective resolution from the ground will exceed what any current space telescope achieves in the infrared. More critically, ELT's coronagraphic performance at the small angular separations characteristic of habitable zone planets around nearby stars is projected to significantly outperform what JWST can achieve for the specific geometry of Alpha Centauri. Then there is LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, still in its concept development phase. LUVOIR was explicitly designed from the beginning with one class of scientific objective at its core: the direct imaging and spectroscopic characterization of exoplanets around nearby sun-like stars. Its coronagraph architecture was benchmarked against the contrast requirements for detecting Earth analog planets around stars like Alpha Centauri A, not inspired by the 2025 episode designed before it, but given a new level of political and scientific urgency by it. If you were designing the ideal telescope to resolve the Alpha Centauri mystery, what capability would you prioritize first? Space-based interferometry represents the third avenue, and the most technically ambitious. The concept involves deploying 2 or more space telescopes in coordinated orbits separated by distances of thousands of kilometers, then combining their collected light through a process called long baseline interferometry. The result is a virtual telescope whose effective resolving power is set not by any single mirror's diameter, but by the physical separation between the spacecraft. 2 telescopes 10,000 kilometers apart function, in terms of angular resolution, like a single mirror 10,000 kilometers wide. The analogy for how this works is elegant. Human beings localize sound with 2 ears. The brain measures the tiny time difference between a sound wave arriving at the left ear versus the right, a difference sometimes smaller than 1/10,000th of a second, and uses that delay to determine the sound's direction with remarkable precision. Interferometry does the mathematically equivalent thing, with light waves arriving at 2 spatially separated detectors. The delay encodes directional and structural information about the source that no single aperture instrument could extract, applied to a planetary system 4.37 light-years away. Space interferometry could achieve the angular resolution to directly image not just the presence of a planet, but the large-scale structure of its atmosphere. The Alpha Centauri episode reached the U.S. congressional budget process in a way that few purely scientific developments manage. During the 2026 NASA authorization hearings, multiple members of the House Science Committee specifically cited the episode, the discovery, the non-detection, the blinker, as evidence that the agency's current instrument portfolio was inadequate for a class of scientific questions that the public demonstrably cared about deeply. The phrase, "We need better tools to answer this question," appeared in the formal hearing record. Budget allocations for the Habitable Worlds Observatory concept, the current NASA flagship mission study that supersedes both LUVOIR and HabEx as the next recommended large space telescope, were referenced in the context of Alpha Centauri explicitly. Private funding moved faster, as it often does. Breakthrough Starshot, the initiative to develop laser-propelled miniature spacecraft capable of reaching Alpha Centauri in approximately 20 years, received additional private investment commitments following the 2025 episode, with the stated rationale that before sending any probe to the system, humanity needed higher confidence about what was actually there. The discovery and subsequent mystery had, paradoxically, made the case for prior reconnaissance more compelling rather than less. You invest more carefully in a destination when you know it has surprises waiting. The instrument that will ultimately resolve whether Alpha Centauri A hosts planets. What those planets are, and what the blinker was, does not yet exist in operational form, but it is being built in Chile, in design offices at NASA Goddard and JPL. In the engineering teams working on space interferometry pathfinder missions in Europe. All of them shaped, in some measure, by the specific failure modes and specific surprises that the 2025 through 2026 campaign exposed. ELT's METIS instrument may detect molecular oxygen and water vapor directly in an exoplanet atmosphere for the first time in history, not inferred, not modeled, but spectroscopically measured. That milestone, if it comes, will transform the search for life from a probabilistic argument into an empirical one. Humanity is building the eyes it needs. The neighbor is still there, still bright, still holding its secrets with considerable patience, and perhaps with a degree of satisfaction. We spent 4 centuries unable to look, then looked and found a mystery, then built better instruments to resolve the mystery, and found that the instruments themselves needed to be better still. The cosmos arranged its nearest interesting neighbor in exactly the spot that would require us to become better scientists to see it clearly. But even if ELT and LUVOIR resolve the Alpha Centauri mystery completely, the 2025 event has permanently changed the way humanity thinks about the biggest question of all. Are we alone? Alpha Centauri 2025 was never purely an astronomical problem. It was always something larger, a stress test for the most consequential hypothesis in the history of human inquiry, that life, in a universe this vast, cannot be unique to one small rocky planet orbiting one unremarkable star in one ordinary galaxy among 2 trillion others. The Fermi paradox has a specific shape. Enrico Fermi, lunching with colleagues at Los Alamos in 1950, looked up from his meal and asked, with the casual precision of a physicist, if the universe is full of intelligent life, where is everybody? The galaxy is roughly 13,000 light-years thick and 100,000 light-years across. It has existed for over 13 billion years. Even civilizations expanding at a tiny fraction of the speed of light would have filled it completely many times over by now. The silence is not neutral data. It is a clue that something about our assumptions is wrong. Now bring Alpha Centauri into that frame. If a candidate gas giant planet exists in the habitable zone of the nearest sun-like star to our own one chosen almost at random from the 100 billion stars in the Milky Way, then the Drake equation's 2 most contested parameters shift dramatically. The parameter Frank Drake labeled FED, the fraction of stars that have planetary systems, nudges toward 1. The parameter NEE, the number of planets per system with conditions potentially suitable for life, grows heavier with implication. Every detected planet around a nearby star is a data point against the hypothesis that planetary systems are rare. And if they are common around the nearest star, the statistical inference for the rest of the galaxy compounds exponentially. The paradox tightens. If planets are common, and the building blocks of life are common, amino acids have been found in meteorites, complex organic molecules in interstellar gas clouds, water ice on comets and asteroids throughout the solar system, then life should be common. And if life is common, intelligence is at least possible in many places. And if intelligence is at least possible in many places over 13 billion years of cosmic time, where is the signal SETI? The search for extraterrestrial intelligence has been scanning the sky for intentional radio and optical transmissions for over 60 years. 60 years of listening, not one confirmed detection. The Great Filter Theory offers the most sobering framework for reconciling these two facts. Somewhere between the formation of a star and the emergence of a civilization capable of communicating across interstellar distances, there is one possibly more catastrophic bottleneck: a filter so lethal that almost no lineage passes through it. The question that has divided researchers for decades is whether that filter lies mostly behind us in the improbable emergence of complex cellular life, or the even more improbable emergence of multicellular organisms, or mostly ahead of us, waiting for every civilization that approaches a certain level of technological power. Alpha Centauri touches this question directly. A confirmed gas giant in a habitable zone around a nearby sun-like star would not itself be evidence of life, but its presence would carry a specific implication that cuts through the Great Filter debate. In our own solar system, Jupiter's gravitational dominance has functioned as a long-range shield for the inner planets, deflecting or capturing a significant fraction of the cometary and asteroidal impactors that would otherwise bombard Earth with extinction-level frequency. A Saturn analog orbiting Alpha Centauri A in or near the habitable zone could perform an identical function for any smaller, rockier world sitting closer to the star. The gas giant is not where life lives. It is potentially what makes life possible. Do you believe extraterrestrial life exists? And do you actually want to know the answer? Which raises a question. The 2025 episode brought into sudden focus what else might be orbiting Alpha Centauri A. Invisible to current instruments, waiting behind the glare that 4 centuries of telescopes never penetrated, the gas giant candidate, if real, is not the only object the system could harbor. Rocky planets at smaller orbital radii Earth scale, Mars scale, something in between would be far dimmer, far harder to detect, and precisely positioned in the zone where liquid water could theoretically exist on a surface. Webb never looked for those. The 2025 campaign was not designed to find them. It found something else first, and then lost it, and the smaller, quieter worlds that might share that system were never the direct target. When Galileo turned his telescope toward Jupiter in 1609 and discovered 4 moons orbiting a planet that was not Earth, he did not find life. He found something arguably more important: proof that the Earth was not the fixed center around which all motion revolved. The discovery demolished a cosmology. It did not answer any question about life, but it changed the context in which that question could be asked so completely that nothing was ever the same afterward. Alpha Centauri 2025 may be that kind of moment. Not an answer, a context changer. The first time humanity's best instrument looked directly into the nearest sun-like star system and found something unexpected enough to resist clean explanation, that alone shifts the question from, might there be planets next door, to, what exactly is happening next door? The frame has changed. The conversation is different now. Proxima Centauri b, the confirmed planet orbiting the actual nearest star to our Sun at 4.24 light-years, sits in a radiation environment that strains the imagination. Proxima is a red dwarf, small, dim, prone to violent stellar flares that episodically strip planetary atmospheres and bombard surfaces with ultraviolet and X-ray radiation at intensities that would sterilize any surface unprotected by a strong magnetic field and thick atmosphere. Proxima b's prospects for habitability, despite its position in the nominal habitable zone, are genuinely poor by the metrics current planetary science uses to evaluate such things. Alpha Centauri A is categorically different, stable, sun-like, old enough for planetary surfaces to have evolved toward complexity if conditions permitted. 417 years to look next door, and when we finally looked, we weren't sure what we saw. But we absolutely cannot look away now. And this is where we must face something nobody has been willing to say plainly in any formal paper: a fifth possibility that isn't excluded by the data, not because it is unscientific, but because it is too large to write down. From 417 years of blindness to a signal that confused every expert on Earth. From the loudest science headline of the decade to a mystery that no instrument has fully resolved. The arc of the Alpha Centauri episode doesn't bend toward a conclusion. It bends toward a different kind of clarity, the kind that comes not from finding an answer, but from finally understanding what the right question is. Because the deepest meaning of 2025 is not captured in either possible outcome, neither "we found a planet" nor "we didn't." The real meaning is this: for the first time in human history, we asked the question with equipment powerful enough that the universe had to respond. Not clearly, not cleanly, but it responded. The signal was real enough to generate controversy. The mystery was deep enough to generate 12 independent papers. The data was strange enough to demand instruments that don't yet exist. For 4 centuries before JWST, Alpha Centauri simply refused to engage. In 2025, it finally did something back. What that something was remains unresolved. That it happened at all is the turning point. The generation now in high school, the students sitting in physics and astronomy classes while the blinker data was being analyzed, while the preprint was being downloaded 400,000 times, while researchers on 4 continents argued about 2.3% probabilities, grew up in a world where the search for planets beyond our solar system was not science fiction. It was a funded scientific program with confirmed results. There were 5,500 confirmed exoplanets when the 2025 announcement was made. That number will be larger by the time those students reach graduate school. They are the first generation for whom "does our nearest neighbor have worlds?" is not a philosophical question, but a technical one, with a budget attached and a telescope pointed at it. The enrollment data from the 2026 university admission cycle showed a measurable increase in declared interest in astronomy, astrophysics, and planetary science programs at American universities. A trend that admissions offices at multiple institutions attributed, at least in part, to the sustained public engagement the Alpha Centauri story had generated across the preceding year. Not the clean discovery version of the story, the messy, contradictory, still unresolved version. Students were drawn not to the triumph, but to the open problem. Which world would you rather live in? One that knows for certain life exists elsewhere, or one that knows for certain it doesn't? Something else happened in 2025 that had never happened before at this scale. The ArcShift downloads, the forum discussions, the citizen science analyses collectively. They created the largest active community of public participants in real astronomical data analysis in history. Not people reading about astronomy, people doing it. Working with actual calibrated data from actual observations made by an actual space telescope, running actual software pipelines, finding actual things in the data that trained researchers had not immediately prioritized. That community existed before 2025 in smaller, more specialized forms. The Alpha Centauri episode expanded it by an order of magnitude and demonstrated that open data policies at this level of scientific ambition could mobilize a genuinely useful, distributed intelligence. The comparison that keeps surfacing, in retrospect, is Apollo 8, December of 1968, the first crewed spacecraft to reach the moon's orbit. And on Christmas Eve, as the crew swung around the lunar limb, astronaut William Anders looked out the window and saw Earth small, blue, isolated, hanging in black space above the moon's gray surface. He grabbed a camera. The photograph became known as Earthrise. It didn't show anything new about Earth. Nothing in the image was information that hadn't existed before. But the perspective was new. And that perspective, seeing our entire world as a single object, finite and alone, shifted something in human consciousness that environmental legislation, philosophy, and decades of argument had not managed to shift. The view from outside changed what people thought about the inside. Alpha Centauri 2025 is Earthrise in the opposite direction, not looking back at where we are, looking out at where we might go or at what might be looking back. The perspective is new. The question it generates is not about our planet's fragility, but about our cosmic solitude. And that shift, once made, cannot be unmade. From Galileo's first telescope in 1609 to JWST's launch in 2021, 413 years to build an instrument capable of even attempting this observation. From JWST to the extremely large telescope's first light, approximately 6 years, the pace has changed. The distance between the question and the technology capable of answering it has collapsed from centuries to years. You are alive in the specific sliver of human history when that collapse is happening, not after it, during it. We spent 417 years looking for the neighbor, found something, lost it, found something stranger, and still cannot say what it is. And the most remarkable part is that we cannot stop. But before the final word, there is one thing about Alpha Centauri that almost nobody has mentioned. A truth that was there from the very beginning, sitting in publicly available data. And when you hear it, everything said so far will feel in a very specific way, very small. Throughout this entire story, the detection, the vanishing, the blinker, the 4 hypotheses, the machines being built to look harder and see clearer, there has been one question at the center of everything. Does Alpha Centauri A have planets? That is the wrong question. Not wrong because it doesn't matter. Wrong because it is too small. Because while we were busy asking it, a larger and stranger truth was sitting in the public astronomical record, available to anyone who looked at the right data set, hiding in plain sight with the patience of something that has 417 years of practice at being overlooked. Alpha Centauri is moving toward us. Not metaphorically, not in some poetic sense. Physically, measurably, at a documented velocity of approximately 22 kilometers per second. Relative to our Sun, the Alpha Centauri system is closing the distance between itself and our solar system. This is established astrometric data, not a new discovery, not a hypothesis. It is in every major stellar catalog. In approximately 29,000 years, Alpha Centauri A will reach its closest approach to our Sun, a distance of approximately 3.26 light-years. 3.26, closer than any star has been to our Sun in the past 100,000 years. The question was never whether we can reach it. It is coming to us. Sit with that. The nearest Sun-like star system in the galaxy, the one we have spent 400 years unable to see clearly, the one that produced a signal we cannot explain and a mystery our best instruments cannot resolve, it is approaching. Every year that passes, the gap narrows by roughly 22 kilometers per second, slow by the standards of space travel engineering, fast by the standards of everything else we've discussed. In geological time, it is arriving now. But the second reveal cuts deeper. The light reaching your eyes from Alpha Centauri tonight, if you were in the southern hemisphere, standing under a clear sky, looking at that bright point in Centaurus, left that system 4.37 years ago. The infrared signal that JWST detected and analyzed in May and June of 2025 described the state of that planetary candidate as it existed in 2020 and 2021, not 2025. The observation and the reality were separated by 4 years before the data ever reached a detector. The planet, whatever it is, whether it exists in the form first detected, whether the blinker is a new phenomenon or an instrument artifact or something without a name yet, that object, right now, in the actual present moment, as you process these words, may be in a state that no observation has yet captured. It may have changed. It may have moved. It may be doing something that the 2025 data, the October data, the blinker data cannot tell us, because those datasets are not windows into the present. They are photographs of the past. All of astronomy is, by necessity, the study of how things were, never how things are. Distance in space is inseparable from distance in time. Every photon that travels is a time traveler. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star beyond our system, you see 4 years ago. When the original Hubble Deep Field imaged galaxies at the edge of the observable universe, those images showed light that left its source over 13 billion years ago from objects that may no longer exist in any form recognizable to the cosmology we use to describe them today. We have never, not once in the history of astronomy, seen the universe as it currently is. We see only its history at varying depths, played back to us at the speed of light. Which brings us to the third reveal, the one nobody in the formal literature has been willing to write explicitly, but which follows from the physics with a logic that is difficult to dismiss. If there is a civilization at Alpha Centauri, not assumed, not claimed, simply considered as a possibility consistent with everything we know, and if that civilization has a telescope, they are looking at Earth right now. And what they see is Earth as it was 4.37 years ago. 2021, pandemic year Earth, a planet whose radio emissions, whose city lights, whose atmospheric composition have been detectable by sufficiently sensitive instruments for roughly a century. With a better telescope, larger mirrors, longer baselines, more sensitive detectors, they could look back further. Earth as it was in the year 1000, barely altered from its pre-industrial baseline. Earth 10,000 years ago, at the dawn of agriculture. Earth 100,000 years ago, populated by anatomically modern humans with no cities, no radio, no light pollution detectable across interstellar distances. The further any observer sits from Earth, the further back in our own history their view reaches. At 4.37 light-years, any observer sees us as we were 4 years ago. At 400 light-years, they see the Europe of the early 17th century. At 65 million light-years, the distance of the Virgo cluster any telescope pointed this way would, theoretically, see a planet whose dominant fauna had just been restructured by an asteroid impact. There is no vantage point far enough away that an observer with sufficient resolution would see us, the civilization currently reading this, currently building the extremely large telescope, currently arguing about a blinker in Alpha Centauri data. That version of Earth is still propagating outward at the speed of light, and it has not yet reached most of the universe. We search for signals from other civilizations. We scan radio frequencies, look for laser pulses, analyze atmospheric spectra for the chemical signatures of biology. But our own signal, the electromagnetic footprint of a technological civilization, is radiating outward from Earth right now. And it reaches Alpha Centauri in 4.37 years. Whatever is there, if anything is there, is receiving it, is analyzing it, is perhaps pointing an instrument back in our direction and seeing exactly what we look like from 4 light-years away, 4 years ago. With whatever resolving power their technology permits, JWST looked into Alpha Centauri and found a mystery without a resolution. But the mystery that matters most is not the blinker. It is not the vanishing planet. It is not the 4 wounded hypotheses or the instruments being built to replace them. The mystery that remains after everything else resolves is this: in a universe so large that light takes 4 years to cross the distance to our nearest neighbor, are we connected or are we alone? And is there any meaningful difference between those two states? If the connection travels so slowly that neither party can ever confirm the other has received the message, 417 years after Galileo first turned a telescope toward the sky, we are still looking, still asking, still building better eyes to see what we cannot yet resolve. And that, in the end, is not a failure of science. It is the only honest answer the universe has ever given us. Keep looking.